Okay, the next presentation is from JASPAR. The title is the concept of the test points in in-vehicle optical physical layer standardization for multi-vendorization. The speakers, we have two speakers. One is Keisuke Kawahara-san from the Furukawa Electric, and another speaker is Naoshi Serizawa-san from Yazaki. Welcome to guys. Please on stage.
Hello everyone. I make a presentation on concept of test points in in-vehicle optical physical layer standardization for multi-vendorization from JASPAR. First, I introduce JASPAR. This slide and the next slide are the same as the presentation JASPAR just gave. So I will briefly describe them. JASPAR was established in September 2004. As shown here, JASPAR has a number of working groups. The group presenting at this event is the Next Generation High-Speed Networks Working Group. The Next Generation High-Speed Networks Working Group is considering at automotive SDN, automotive TSN, 10 gigabit per second Ethernet, and SerDes in-vehicle requirements. This slide shows a relationship between the Next Generation High-Speed Networks Group team structure and the OSI reference model. Today, I am presenting on optical physical layer. This is the agenda for my presentation. This slide is an introduction to the Next Generation Technology Study team. JASPAR has been considering 100 megabit per second and 1 gigabit per second automotive Ethernet, FlexRay, and CAN FD. Currently, we are focusing on both electrical and optical Ethernet for automotive applications. Generally, most OEMs are always thinking of EMC, high-speed communication, weight, and CO2 reduction. To meet these requirements, components with high EMC resistance, quick response, broadband, lightweight, and low power consumption are required. We think optics are the best solution. And so, I show the scope of the optical physical layer that JASPAR is considering. Between files for the entire optical physical layer is the object. And the bitrate is 10 gigabit per second. And both glass and plastic fibers with wavelengths of 850 nanometer and 980 nanometer are candidates. The main considerations are shown here. We have started testing two types of pixels, IEEE P802.3CZ and P802.3DH light source candidates. Also, we are considering the test points necessary for each component test and third-party certification for multi-vendorization. We report on these details. JASPAR is considering a multi-vendorization to ensure component procurement stability. And Open Alliance TC7 is considering the test points needed to verify the performance of optical components. The characteristics of the light source are very important in realizing optical communication. Pixel is one of the light sources are very important in realizing optical communications. On the other hand, in 802.3CZ and DH, pixel with different wavelengths 850 nanometer and 980 nanometer are being discussed. So we have started to evaluate the characteristic of commercially available pixels. Pixel is a vertical cavity surface emitting laser. Recently, high-speed modulation devices with bitrate exceeding 10 gigabit per second have become available in automotive environments. Purpose of JASPAR is to confirm that 10 gigabit per second pixels meeting the IEEE standard were available from multiple vendors. As a result, we found that pixels with these specifications are available from VIS and ENEOS. So we have performed these 4 tests, and we will now show the results. The coupling between the pixel and the optical fiber follows the evaluation reported by KD Poff. This slide shows the IVL characteristic of the pixel. A schematic diagram of the IR measurement is shown here. The x-axis is the bias current, and the y-axis shows the optical output power when the current is applied from 0 to 10 milliampere. The ambient temperature is minus 40 to 105 degrees Celsius. The optical output power of 850 nanometer at VIS becomes a peak at a bias current of 5 milliampere at 105 degrees Celsius and decreases at bias current or higher than 5 milliampere. The optical output power of 980 nanometer at ENEOS has an almost linear IR characteristic within the measurement range, but the power consumption is increased due to the large variation of the temperature characteristic of the threshold current. For the IV measurement, we use the same schematic diagram as IR measurement, but the y-axis shows the forward voltage. The forward voltage of 850 nanometer at VIS has a small variation in differential resistance against temperature, allowing for high-speed communication. The forward voltage of 980 nanometer at ENEOS increases when ambient temperature is low. This slide shows the frequency response and RIN, relative intensity noise of the pixel. A schematic diagram of the frequency response measurement is shown here. The x-axis shows the frequency, and the y-axis shows S21 insertion loss, when the frequency is switched from 0 to 20 gigahertz with a bias current of 4 milliampere. The ambient temperature is minus 40 to 105 degrees Celsius. Both frequency response was confirmed, same as specifications. A schematic diagram of the RIN measurement is shown here. The x-axis shows the extinction ratio, and the y-axis shows RIN OMA. The relative intensity noise results obtained in the extinction ratio range of 3 to 5 dB are smaller at 850 nanometer than at 980 nanometer. So the signal-to-noise ratio is higher at 850 nanometer. This slide shows the I pattern for 10 gigabit per second energy operation. A schematic diagram of the I pattern measurement is shown here. The I pattern was measured at I bias 4 milliampere and ambient temperature of 25, 105, and minus 40 degrees Celsius using VCSEL at 850 nanometer and 980 nanometer. The waveforms are shown in yellow as obtained by the photodetector. Green after DFE processing, red after applying a fourth-order Bessel filter in addition to DFE, and blue after FFE processing. For 850 nanometer, a sufficiently large eye aperture is observed, even in the low waveform, and further expansion of the eye aperture can be observed by applying various types of DSP. At 980 nanometer, this distortion of the low waveform is not noticeable at high and low temperature, but sufficient eye aperture can be observed by applying various types of DSP. In both 850 and 980 nanometer wavelengths, we have confirmed that 10 gigabit per second VCSEL met the IEEE standard were available from multiple vendors. This is a summary of the VCSEL test. JASPAR has tested 2 VCSEL chips. Both VCSELs were confirmed to be the same as their catalog specifications. We think it is necessary to evaluate the actual system performance and optimize the ranging optical condition, pixel bias current, and optical waveforms DSPs, etc. If this can be achieved, the VCSELs confirmed in this test may be applicable to automotive applications.
So, okay, this is my turn, and I'd like to introduce about why the standardized test points are needed. So, currently the ISO 21111 series, which is specify the Ethernet technologies, like here, and special test point like TP1 to TP4 here. On the other hand, the IEEE 802.3 committee, and they also specify the test point of the TP1 to TP4. And the reason why we need the test point is to evaluate the system, as well as the component level. And also, the interoperability is needed. Then the third-party certification is required. But in that case, this third party needs a test point and requirement, specification, whatever. Otherwise, they cannot evaluate or confirm anything. So then the ISO and the IEEE defined test points are required for component evaluation and third-party certification. This is the reason why we need a test point and discussing in JASPAR. Okay. Then, on the other hand, we are thinking about the use cases of the Ethernet technology for automotive application. We have thinking about the 4 kinds of the use cases. The one is smart head and plug. It means the integrated PMD, PCS, and driver TIA looks like here, and only for the coupling the devices and optical fiber each other. And This one is also a little different one. But the smart head and plug, the separated PMD, PCS, and driver TIA. So normally, the name the Phi chip, which developed many manufacturers in case of the electrical communication system. And sometimes the PCS PMD driver generates the analog signal or digital signal and transfer to the other. But the fiber optic technology, we need to electrical optical converter in order to change the electrical signal to optical signal by using a driver, and also the opposite side is a TIA to the photodiode. So in that case, this one is a separate component. Then we need to have some test point between the PCS, PMA, and the drivers. Yeah. And also the active optical component named AOC, which is the integrated fiber optics technology inside one connector and separate from the ECU. The ECU has only the electrical connector and just made the connector in between by using the standard connector, but the communication channel is by optical. So finally, the active optical components separate the PMD, PCS, and the PMD driver means the so named the Phi chip is integrated the ECU unit, but the electrical signal by using the electrical connector and the fiber optics component element is integrated this one. So in that case, we can specify the test point like here, but only that use case of number 3, it's harder to specify the test point because this is one component and this is one component, so that the interface is a serial signal to the serial signal. So, and no test point can be defined at the moment. But we are thinking about several use cases for the standardization activities as well. Okay, and I'm a little bit break down the function. So the function is here, maybe you are familiar with about it, but between the PCS, PMA, and PMD, physical media dependent, need to have some interface. In that case, we need the test point TP1 name. And also the interface of the ECU, like connectors or something like that, and harness, so that the TP2 is needed. But sometimes it is difficult to measure the directly, but without using optical fiber, then we specify the TP2C here with 1 meter cables, for example. And also the TP3 means the other side of the optical connectors. And then the TP4 is similar to the TP1, which is a test point between TIA. TIA means convert from the current to the voltage, and TP4 is needed to be specified. In that case, the definition of the TPs are necessary for uniform evaluation. I mean, we are also thinking about the interoperability, of course. Then these test points will be needed, but depends on the solution. And furthermore, we are going to describe, and also I'd like to explain about the third-party certification. So test point once defined in the interface requirements. And you know, every time the input and output condition are component is necessary, because every test has to be need the input condition and DUT and output condition, and compare to the standard specification to the output results. So in case of the fiber optic technology, the TP1, for example, the electrical signal into the optical device. So the driver and VCSEL generates the optical signal to the outside. And IEEE also specified the TP2B. In that case, output result can be measured like this way and compare to the specification. If the TP2B specification is satisfied by using the TP1 condition, this DUT is confirmed to the, or comply to the international standard, something like that. And also, we are continuously to measure the DUT like optical harness, for example. So TP2B condition is also specified as standard and input the optical signal to the optical harness and can be measured or detected the opposite side, and test result can be obtained. So, and IEEE also specified the TP3 as well, so that we can compare the result and the TP3 specification, and if the meet the criteria or something like that, the results, then this DUT can be comply to the international standard specification. So if each part satisfies the TP requirements, the communication established over the entire system can be confirmed. So this one component comply and comply, then the total system can be complied with the specification. This is the idea for the third-party certification. But the supplier is totally different. One supplier provides a connector, one supplier the harness, but nobody can meet the old system before assembling the vehicle. So that the supplier only provides a device or harness to the OEM, and in the OEM manufacturing can meet all together, but the OEM never know and the system is good or not. But each component has to be meet the specification, then the total system can be good enough for the standard. It's the idea. And so maybe the last one is third-party certification procedure. So normally the standardization body develop the standard. And this is, I'm sorry, this is a typo. Supplier and tester house, of course, the end user like OEM sit together to develop the standard, international standard. And then once the standard is developed, then this standard has to be disclosed to the supplier, tester house, and the end user. Okay. And once the end user wants to use the Ethernet technology, for example, then the tester house and the end user will agree the part permission approval condition, which is complied to the international standard, for example. And then end user requests the supplier, tier 1, tier 2, tier 3, blah, 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 and indicates the requirements. Then the supplier will develop the component and request third-party certification like here. And then once the house measure each component and comply to the standard, then their test house will issue the certification report, which is good enough or meets the specification validation. So enable to ensure the established overall communication even when the parts from different suppliers are connected, but this kind of scheme is good enough and working, then automatically validate each component meets the specification. So currently the JASPAR is also working with test house, not test house, working with or collaborate with the Nagoya Institute University, and they are the one of the test house to be and measure about every testing by optical, like time domain or flexion domain or optical domain evaluation, as well as the electrical Ethernet complied to the TC9. So both the optical and the electrical component, they have their own test specification and each component requirement. Therefore, the Nagoya Institute University can support and release some certification report in next March, from next March. Now, preparing this kind of the evaluation system. Okay, so Nagoya Institute University, the Future Communication Research Center, sorry, contribute the basic research, standardization, and test house activities in order to contribute to the enhancement of the reliability of in-vehicle communications. So this is a very brand new center and operate from next March. And if you are interested about it, please access to this URL. Okay. So this is conclusion. What I told you today. The optical components have the high EMC resistance and able to communicate at high speed and able to reduce CO2, as I mentioned. And also, VCSEL has a good performance from -40 to 105 degrees Celsius temperature environment, and confirm the VCSELs are applicable for in-vehicle applications. We confirmed. And test point definition is mandatory for the component test to be guaranteed for network system. And establishing test house at Nagoya Institute University in Japan. So the preparing to install optical communication system at any time. So this is a presentation from JASPAR. Thank you very much for your attention.
Thank you, Kawahara-san and Serizawa-san for nice presentation. Do you have any questions to this? Okay, nothing. So can I ask one question? Maybe many people are interested in. So the Japan JASPAR is actively operate this kind of activity for the optical Ethernet. Are you JASPAR going to use optical Ethernet for the Japanese vehicle?
So, and I think it's a good question. So the JASPAR is not only focusing about fiber optic technology. As I previous presentation we did, JASPAR also looking at the both technology like copper solution and optical solution. But if the OEM want to use one solution, all of the requirements and the test standard and specification is available, is good enough for the to OEM supporting. That's why we are developing on thinking about both technologies at the moment.
Okay, understood. Yes, please.
Yes, hello, Haitham Kadri with Molex. You mentioned TC9.
Yeah.
TC9 is more copper.
Yes.
So is JASPAR planning on aligning with Open Alliance TC, I think 17 is the technical committee they opened. Is that the plan?
Mm-hmm. So, I must apologize, but I don't know about the TC17.
No, the TC16 maybe.
16, sorry? So one of the technical committees in Open Alliance. Are you planning on aligning with the technical committee in Open Alliance for optical?
So currently, I think at the moment in the Open Alliance, the TC7 is only the...
Oh, TC7?
Yeah.
Okay, apologies. I didn't realize the number, but
okay.
you said TC9, so I was wondering, are you aligning with the optical technical committee?
TC9 looking at only for the electrical, and
okay.
TC7 looking at optical.
Okay.
So that the Nagoya Institute University can support the TC7 as well as TC9.
Okay, so you're aligning with the Open Alliance?
Yeah.
Okay, that's what I wanted to double check. Thank you.
Thank you very much.
Any other questions? Please show us page 17. So may I ask one question for the clarification? Yes, so here shows the test point 2C here, which is on the cable. For what this test point
is needed?
Yeah.
Okay, so actually this point is the interface between ECU and the optical harness, and of course we can measure the directly from here. TP2B is possible. We don't care about it. But sometimes the optical output has to be measured by using optical fiber in order to connect the test equipment. That's why we need to have short fiber in order to connect to the test equipment. That's why this test point TP2C is defined in Open Alliance, not IEEE, I think.
Okay, understood. So let me we take a coffee break. So thank you for Kawahara-san and Serizawa-san. Thank you.